Okay, so this is week 1 of Lent term, and this is the second lecture of this first week of the Lent term. And last time we recalled what equivalence relations were, because that's going to play an important role in this chapter. And we began our discussion of the natural numbers. We gave the Peano axioms for a set n and a function which is then called the successor function. And then we were able to give the definitions of addition and multiplication in the set of natural numbers, and we proved some properties such as commutativity and associativity of addition and multiplication. And in the exercises you will also see a proof of the distributive law, that multiplication distributes over addition. So today we will finish our discussion of the natural numbers by talking about the order relation on the set of natural numbers. So what it means to say that one natural number is less than another natural number. We'll give a definition of that. And then we'll prove this important property of this order relation, which is called the Trichotomy Law. And we will also prove something known as the well-ordering principle. And then we'll also begin our discussion of the set of integers. Okay, so let's first give the definition of what this order relation is. So suppose that little k and capital K are two natural numbers. Now if there exists a natural number m such that when added to this little k you get this capital K, then we write that little k is strictly less than this capital K. Or sometimes we also use the notation that capital K is strictly bigger than this little k. So as an example, we know that 1 plus 1 by the definition of addition is the successor of 1, which we call 2. And so to 1, when we add this natural number, you get 2. So it follows that 1 is strictly less than 2. Now for this order relation, we will prove this important property, which is called the Trichotomy Law. So this is a theorem that we'll soon prove. And that says that for any two natural numbers, one and only one of the following three statements holds. M is equal to n, or m is strictly less than n, or n is strictly less than m. So what this means is that, first of all, given any two natural numbers, one of these three statements has to hold, and only one of these statements can hold. So it can't be that both this case as well as some other case is true. Okay, so exactly one of these three statements holds. And we will soon prove this, but to prove this we will use an auxiliary result, which we call this lemma, which says that if m and n are any two natural numbers and you add n to m, then the result can't be equal to n. So before proving the trichotomy law, we will prove this lemma, which says that if m and n are natural numbers, then m plus n is not equal to n. So to do this, we will consider the following set, which is the set of all k's, natural numbers, such that m plus k is not equal to k. Now if we manage to show that this S is the whole set of natural numbers, then in particular the given n will also belong to it, and so m plus n is not equal to n will follow. So the aim is to show that this S is the whole set of natural numbers, and to do this we will use the induction axiom. So we'll show that 1 belongs to S, and whenever k belongs to S, its successor also belongs to S, which will allow us to conclude that this set S is the whole set of natural numbers via the induction axiom, and then we'll get in particular that m plus n is not equal to n. So that's the plan. So we want to show that this S is the whole set of natural numbers. So first of all, 1 belongs to S. Well, to show that 1 belongs to S, we have to show that m plus 1 is not equal to 1. But if it was equal, then we will have that m plus 1 is 1, but this m plus 1 by the definition of addition is the successor of m. So then we would get that 1 is the successor of something which violates the first Peano axiom. So we get a contradiction if m plus 1 is equal to 1. So this cannot hold, so m plus 1 is not equal to 1. In other words, 1 belongs to S. Now let us assume that k belongs to S, and we'll show that its successor also belongs to S. Okay, so since k belongs to S, we already know that m plus k is not equal to k, and we want to show that its successor belongs to S. So we want to show that m plus sigma k is not equal to sigma k. So let's start with the left hand side. M plus sigma k, well, by the definition of addition, so m plus the successor of something will be the successor of m plus the thing inside. So M plus sigma k is the successor of M plus k. Now we know that M plus k is not equal to k because k belongs to S. And since sigma is injective, it then follows that if I apply sigma on both sides, the images will also be different. So we know that sigma M plus k is not equal to sigma k. Okay, so that follows because of the injectivity of sigma. So this sigma M plus k is not equal to sigma k, and so we have got that M plus sigma k is not equal to sigma k. So sigma k belongs to S, and so we have proved this statement. So we know that 1 belongs to S, and whenever k belongs to S, sigma k belongs to S. So by the induction axiom, it follows that S is the whole set of natural numbers. Okay, and so in particular, the given n, which belongs to the set of natural numbers, belongs to S, and so m plus n is not equal to n. So this proves this lemma. So we are now ready to prove the trichotomy law, which says that if m and n are any two natural numbers, then one and exactly one of the following three statements holds. M is equal to n, m is strictly less than n, or n is strictly less than m. So we have this trichotomy. So in the proof, we'll first show that at most one of these statements can hold, and then we'll show that one of them has to hold. So let's first show that at most one of these statements can hold. So no two can hold simultaneously. So let's first show that if 2 holds, then 1 cannot hold. Well, if 2 holds, that means that there exists a natural number k such that when added to this m, you get n. So m plus k is equal to n. But by the lemma that we just showed, m plus k can't be equal to m. So n can't be equal to m. So we have got that 1 cannot hold. So this means that if 2 holds, then 1 cannot hold. Almost the same proof shows that if 3 holds, then 1 cannot hold. And then we also get the contrapositives of these. That is, if 1 holds, then 2 cannot hold, and if 1 holds, then 3 cannot hold. So it remains to show that 2 and 3 cannot hold simultaneously. So suppose that 2 holds, and let's suppose that 3 also holds. So 2 holds means that there exists a natural number k such that m plus k is equal to n, and 3 holds means that there exists a natural number L such that n plus L is equal to m. Now, if you look at what is m plus k plus L, this m plus k is nothing but n, so you can replace this m plus k by n. So this becomes n plus L, but n plus L is again equal to m. So you get that m plus k plus L is equal to m. But by the associativity of addition, you can club these two together. So you get m plus k plus L is equal to m. And k plus L is some natural number. So you get m plus some natural number is equal to m, but that can't happen by the lemma. M plus any natural number is not equal to m. So we get a contradiction. And so if 2 holds, then 3 cannot hold. And the contrapositive of that is that if 3 holds, then 2 cannot hold. So 1, 2 and 3, they are mutually exclusive. So at most one of these statements can hold. So next we'll show that one of them has to hold. Okay, so we have to show that given the m and n, you have that either m is equal to n, or m is less than n, or n is less than m. So to do this, we will consider the following set S, which is the set of all the natural numbers k, such that either m is equal to k, or m is less than k, or k is less than m holds. Now, if we manage to show that this S is the whole set of natural numbers, then the given n, being a natural number, will belong to this S, and so for that n, either m is equal to n, or m is less than n, or n is less than m holds. So the plan is to show that this set S is the whole set of natural numbers, and then we'll be done. So to do this, we will use the induction axiom. So we'll show that 1 belongs to the set, and whenever k belongs to the set, also its successor belongs to the set. And then via the induction axiom, we'll be able to conclude that S is equal to n, and this will imply in particular that n belongs to S, and so we'll be done. So that's the plan. So let's begin by showing that 1 belongs to S. Now if m happens to be equal to 1, then m is equal to 1, and so we are in this case, so statement 1 holds, and we are done. And if m is not equal to 1, then last time we proved this theorem which says that every natural number not equal to 1 has a predecessor. In other words, every natural number not equal to 1 is the successor of something. So if m is not equal to 1, then m is the successor of some natural number L. In other words, it's L plus 1. And so to this 1 I have to add some natural number to get m, and so 1 is strictly less than m. So in other words, statement 3 holds. And so in this case also one of these three things holds, and so 1 belongs to S. Now let's show that whenever k belongs to S, its successor also belongs to S. Now if k belongs to S, we already know that one of these three cases holds, that either m is less than k, or m is equal to k, or k is less than m. So let's analyze these three cases individually, and in each case we will show that also the successor belongs to the set. So if m is strictly less than k, let's consider that case first. What does that mean? That means that there exists some L, natural number, such that m plus L is equal to k. But I want to say something about the successor of k. So it would be nice to add 1 to both sides so that we get the successor of k over here. So if I add 1 to both sides of this, we get m plus L plus 1 is equal to k plus 1. K plus 1 is the successor of k. And over here, I can use associativity to club these two together, and then it becomes the successor of L. So to m, I have to add a natural number to get sigma k. In other words, m is less than sigma k, and so we are in this case 2 for this sigma k replacing k. Right? So statement 2 holds, and so in this case we are done. Now let's suppose that m is equal to k. Suppose we are in that case. Well, again, let's add 1 to both sides. So you get m plus 1 is k plus 1. K plus 1 is nothing but the successor of k. So to this m, I have to add 1 to get sigma k. So m is strictly less than sigma k. So we are in this case 2 when the k replaces sigma k. So in this case also we are done. And finally, let's consider the case when k is strictly less than m. So in that case, we know this means that there exists a natural number L such that k plus L is equal to m. Now let's analyze the two cases when L is equal to 1 or L is not equal to 1 separately. If L is equal to 1, then this says that k plus 1 is equal to m. In other words, sigma k is equal to m. And then we are in case 1, you see, with k replaced by sigma k. And so in this case we are done. And if L is not equal to 1, then, well, by this theorem we know that it has a predecessor. So this L is the successor of some natural number L prime. Okay, and then this equation k plus L is equal to m, well, we have just discovered that this L is the successor of something. So you get k plus the successor of this L prime is equal to m. But successor of L prime is nothing but L prime plus 1. So you get k plus L prime plus 1 is m. But by using the various laws of addition, this 1 can be clubbed together with this k, so that then this becomes k plus 1, which is the successor of k, plus L prime is equal to m. So to sigma k, I have to add a natural number to get m. In other words, sigma k is strictly less than m. So case 3 holds, with k here replaced by sigma k. And so in this case also we are done. So in each case, this, or this, we have shown that sigma k also belongs to S. So we have proved this statement. And so by the induction axiom, since 1 belongs to S and whenever k belongs to S, we know that its successor also belongs to S. It follows that this S is the whole set of natural numbers. Now if I take the given n that belongs to this set of natural numbers, so it also belongs to S. So one of these three cases has to hold for the n. So either m is equal to n, or m is strictly less than n, or n is strictly less than m holds. So that completes the proof of this trichotomy law. Okay, so we have now seen the proof of the trichotomy law, and what we'll do next is to learn about the well ordering principle and prove it. So what does the well ordering principle say? It says that if you have a non-empty subset S of the set of natural numbers, then this S has a least element. In other words, the minimum of S exists. So let's first explain what's meant by a least element of the set S. So here is the definition. Let S be a non-empty subset of the natural numbers, then an element L belonging to S is a least element of S if for every n belonging to S you have that L is less than or equal to n. So this symbol means less than or equal to. So L less than or equal to n means either L is strictly less than n or L is equal to n. So this L is a lower bound of S but it should also belong to S, and then it's called a least element of S. Now, to prove this well-ordering principle, we will need first the following auxiliary result, which we call this lemma, and that says that for every natural number n, you have that 1 is less than or equal to n. So let's first prove this lemma. So to prove this lemma, we will consider the following set S, which is defined to be all those natural numbers n such that n is bigger than or equal to 1. So that's the set S. Now, if we manage to show that this S is the whole set of natural numbers, then we would be proving exactly the claim in this lemma. So that's the plan, to show that this S is the whole set of natural numbers, and to do that we will use the induction axiom. So we'll show that 1 belongs to S, and whenever n belongs to S, also its successor belongs to S. Now the fact that 1 belongs to S is obvious because 1 is equal to 1, so it's of course less than or equal to 1 also, and so 1 belongs to S. Now if n belongs to S, we want to show that its successor also belongs to S. Now if n happens to be equal to 1, then the successor of this n would be 1 plus 1, and so to 1 I have to add something to get sigma n, and so 1 is strictly less than sigma n, and so it's also less than or equal to sigma n, so this holds with n replaced by sigma n, and so sigma n belongs to S in this case when n is equal to 1. But if n is in S, then we know that 1 is less than or equal to n, so either it's the case that 1 is equal to n or 1 is strictly less than n. So let's see what happens when 1 is strictly less than n. We have already covered the case when n is equal to 1, and now we consider the only other possible case, namely 1 is strictly less than n. Now if 1 is strictly less than n, then what does that mean? That means that to 1 I should add some natural number k to get n. So 1 plus k is equal to n. So this means that sigma k is equal to n. Now I would like to see sigma n over here, and to get that I can add 1 on both sides. So if I add 1 on both sides, I get sigma k plus 1 is n plus 1, which is sigma n. So to 1 I have to add a natural number to get sigma n. In other words, 1 is strictly less than sigma n, so 1 is less than or equal to sigma n, and so this holds with n replaced by sigma n. So again I have got that sigma n belongs to S. And so whenever n belongs to S, we have shown that sigma n belongs to S. Moreover, we also know that 1 belongs to S. So by the induction axiom, S is equal to n, and that proves the statement of this lemma, that for all natural numbers n, 1 is less than or equal to n. Okay, so we'll now show the well-ordering principle, which says that if S is any non-empty subset of the natural numbers, then S has a least element. So to prove this, we will consider the set lambda, which is the set of all lower bounds of S. So it's the set of all natural numbers L, such that for every n belonging to S, L is less than or equal to n. And we will show several things about this lambda. First, we'll show that 1 belongs to lambda. Then we'll show that lambda is not the whole set of natural numbers. Now, if it was the case that for every L belonging to lambda, its successor also belonged to lambda, then by the induction axiom it would follow that lambda is the whole set of natural numbers, which we know is not the case. And so this cannot hold. So that means that there must be a bad L star belonging to lambda whose successor does not belong to lambda, and this L star will be the least element that we seek. Okay, so we'll show all this. So let's first start by showing these properties of lambda. So first of all, we claim that 1 belongs to lambda. Well, for that to hold, 1 should be a lower bound of S. In other words, 1 should be less than or equal to n for every n belonging to S. But by the lemma just shown, we know that 1 is less than or equal to all natural numbers n. So in particular, all the natural numbers which lie in S. So 1 belongs to this lambda. Now let us show that lambda is not the whole set of natural numbers. So let's take any element n belonging to S. Then n plus 1 is the successor of n. And so to n I have to add this natural number to get sigma n. So we know that n is strictly less than sigma n. Then by the trichotomy law, it follows that it is not the case that sigma n is less than or equal to n, because this prevents that from happening. So this means that this sigma n is not less than or equal to all the elements of S, because here is an element of S such that it is not the case that sigma n is less than or equal to n. So this means that sigma n is not a lower bound of S. And so we have that this lambda is not the whole set of natural numbers, because if you take such a n in S, S is non-empty, then we have that its successor is not a lower bound of S. Okay, so lambda is not the whole set of natural numbers. Now, let's suppose that for every L in lambda, its successor also belongs to lambda. Then by the induction axiom, it follows that lambda is the whole set of natural numbers, which we know is not true. So this cannot hold. So it is not the case that for every L belonging to lambda, its successor belongs to lambda. That means that there must be a bad L star which belongs to lambda, whose successor does not belong to lambda. So what do we know about this L star? Right now we just know that it's in lambda. So all we know is that this L star is a natural number. But what we want is that this L star should be an element of S. So that's the task we have to do. So what we know is that this L star is an lower bound. So that means that for all n's belonging to S, L star is less than or equal to n. And what we want to show is that L star is in S. So let's suppose that L star is not in S. Now what we know is that for every n belonging to S, L star is less than or equal to n. But you see, it cannot be equal to n because then it would belong to S. So the only choice which is left by the trichotomy law is that for every n belonging to S, this L star must be strictly less than n. Now let's show that then this somehow implies that L star plus 1 is less than or equal to n. Okay, so let's prove that over here. So this is the highlighted thing which corresponds to this implication, the justification of this implication. Okay, so what do we know? If I take any n in S, we know that L star is strictly less than n. That means that there exists some natural number k such that L star plus k is equal to n. Now there can be two choices, either k is equal to 1 or k is not equal to 1. If k is equal to 1, then this reads that L star plus 1 is equal to n. So it's of course less than or equal to. So this holds then. So this case is done. So now let's suppose that k is not equal to 1. Then by the theorem, we know that every natural number not equal to 1 has a predecessor. In other words, every natural number which is not equal to 1 is the successor of something. So this k, when it is not equal to 1, is the successor of some L. Okay, so sigma L is equal to k. So that means that L star plus sigma L is equal to n. But this sigma L is L plus 1, and that 1 that you get, you can attach to L star. So you get L star plus 1 plus L is equal to n. In other words, L star plus 1, you have to add a natural number to it to get n. So L star plus 1 is strictly less than n, so it's certainly less than or equal to as well. So what we have got from here, we have justified this implication, and we have got that for every n belonging to S, L star plus 1 is less than or equal to n. In other words, we have shown that sigma L star is less than or equal to n. But that's a contradiction, because then sigma L star would be a lower bound of the set S, and so it would belong to lambda, whereas we know that it does not belong to lambda. So this contradiction shows that this assumption cannot be true. So L star has to belong to S. So we have got an L star which is a lower bound, and moreover it belongs to the set S, and so this S has a least element. So that concludes our discussion of the natural numbers, and now we will start our discussion of the integers. So before we give the definition of the set of integers and the construction from the natural numbers, let us give some motivational remarks about why this set is required of integers. So let us suppose that m and n are natural numbers, and let's consider the equation m plus x is equal to n in the unknown x, which should be a natural number. Now if m is strictly less than n, that means that there exists a natural number which when added to m gives n. In other words, this equation has a solution. On the other hand, if this equation has a solution in the set of natural numbers, then there exists a natural number which when added to m gives n, so m must be strictly less than n. So this equation is solvable in the unknown x if and only if m is strictly less than n. But suppose that for arbitrary m and n, I want to solve this equation. Well, clearly that's not possible because there is this arithmetic hurdle that m should be strictly less than n. But maybe there is a bigger set of numbers than the natural numbers, let's call them integers for now, such that if you view the m as an integer, the n as an integer, then there exists a solution in the set of integers. So this x is then an integer, but what should this x be? Well, we know that it should be n minus m, but as yet we don't know what this minus means. But it is some x which is associated with this equation. The data given is m and n. M is on the left hand side, n is on the right hand side, and then the x which wants to be n minus m is associated with this equation. So we think of it as an ordered pair m comma n because it comes from this equation. But then if we think of this x as an ordered pair, then that same x should also be associated with this equation, because to this equation if I add 1 on both sides, then I get m plus 1 plus x is n plus 1, and the same x should do the job because this equation is just obtained from this equation by adding 1 on both sides. So this x should also be associated with the pair m plus 1 comma n plus 1. So as an integer, this ordered pair should be indistinguishable from this one. And I can keep playing this game. So I can add 1 again, and the same x should also be associated with the ordered pair m plus 2 comma n plus 2, and so on. So somehow, if you view this ordered pair as the integer x, then that x should also be associated with this ordered pair and this ordered pair and so on. So somehow all of these ordered pairs are indistinguishable as an integer. So this suggests that, well, they are equal in some sense. That reminds us that perhaps they are equal under an equivalence relation, and then all these ordered pairs are really in the same equivalence class. So they are one and the same thing, and the integer should really be then the equivalence class containing that ordered pair. Okay, so all this is wishful thinking. The first question is, what should such an equivalence relation be? Well, if you have an ordered pair m comma n, that should be indistinguishable from everything which appears in this list. Suppose that m prime and n prime appear in this list. Well, how does something appear in the list when you add the same natural number to both m and n? So this m prime and n prime which appears in this list should be such that m prime minus m should be the same as n prime minus n. So m and n should be equivalent to m prime comma n prime if m prime minus m is n prime minus n, but as yet I don't know what this minus means. So let's write it in a way which is familiar to us. So bring this m to this side and n to this side, and then we will get m plus n prime is n plus m prime. And now I'm just working with natural numbers, so this is a well-defined thing. So we define the equivalence relation, we'll see later that it's an equivalence relation, on the set of all pairs of natural numbers in this way. M comma n is related to m prime comma n prime if m plus n prime is n plus m prime, and then the equivalence class containing this mn we'll check is in fact exactly this list. And so the integer which solves this equation should be really thought of as the equivalence class containing the ordered pair m comma n under this equivalence relation. And such equivalence classes which are obtained is then to be thought of as the set of all integers. Okay, so these were just motivational remarks. We were not very precise about many of the remarks that we made, but now we will start the development precisely. We'll give precise definitions. And had we done the development just by starting with the definitions, we wouldn't know where it all came from. So this is sort of the motivation for that. So now we'll start with the precise definitions. So here is the definition of the relation tilde. So let n, m, n prime, m prime be natural numbers, then the ordered pair m comma n is related to m prime comma n prime if m plus n prime is n plus m prime. Okay, and the way to remember this thing is that, well, you join these two and you add them up, and the inner and you add them up, and the sum should be the same. Okay, so let's first check that this tilde is an equivalence relation. So we have to check reflexivity, symmetry and transitivity. For reflexivity, we have to check that whenever Mn is a pair of natural numbers, that's related to itself. Well, what should happen for it to be related to itself? This sum, m plus n, should be this inner sum, n plus m. But by commutativity, this is of course true of addition. So reflexivity is alright. For symmetry, we have to check that if Mn is related to m prime n prime, then m prime n prime is related to Mn. So well, Mn related to m prime n prime already tells us that m plus n prime is the same as n plus m prime. But this means that if I read it from right to left, you have m prime plus n is equal to n prime plus m, right? But that's the same as saying that m prime n prime is related to mn, indeed, because what would this mean? That would mean that m prime plus n, which is this thing, should be equal to n prime plus m, which is this thing. So symmetry is also alright. Finally, let's check transitivity. So suppose that mn is related to m prime n prime and m prime n prime is related to m double prime n double prime, and what we want is mn is related to m double prime n double prime. From this we know that m plus n prime is n plus m prime, and from this we know that m prime plus n double prime is the same as n prime plus m double prime. Now if we simply add these two, you see that there are some common things, these highlighted things. This pink one with this pink one, they match, and this one matches with this one. So what we'll get is m plus n double prime plus m prime plus n prime is the same as n plus m double prime plus n prime plus n prime. So this m prime plus n prime is something in common on both sides. So it's tempting to cancel these two. So we would like a cancellation law for addition. So let's quickly prove that. Let's prove that if a, b and l are natural numbers such that a plus l is b plus l, then this implies that a is equal to b. Well, let's just use the trichotomy law. We will show that it's not the case that a is less than b, and it's not the case that b is less than a. So the only choice is that then a has to be equal to b. Well, let's suppose that a is strictly less than b. What does that mean? That means that there exists a natural number k such that when added to a you get b. But then if I add l to both sides, I'll get a plus l plus k is b plus l. But that means that to a plus l I'm adding a natural number to get b plus l, and so a plus l is strictly less than b plus l. So a plus l cannot be equal to b plus l by the trichotomy law. So we have arrived at a contradiction, and so this cannot happen. And the case when b is strictly less than a is exactly similar. You just swap the a and b. Okay, so by this cancellation law, then we are allowed to cancel these two, because you think of this as the a, this as the b, and this as the l. So by what we have just shown, it follows that m plus n double prime is equal to n plus m double prime, which exactly means that mn is related to m double prime n double prime. After all, what would this mean? This would mean that m plus n double prime, which is this thing, is equal to n plus m double prime, which is this thing. So the relation is also transitive, and this proves this theorem. So this tilde is an equivalence relation. The integers will be equivalence classes under the equivalence relation that we have just discussed. So let's see what the equivalence classes look like. So as usual, n times n is the Cartesian product of n with itself, and it's the collection of all ordered pairs m comma n, where m and n are natural numbers. So for such an ordered pair m comma n, the equivalence class containing this ordered pair is the set of all ordered pairs m prime n prime of natural numbers such that mn is related to m prime n prime. So if we translate what this equivalence relation means, this means that m plus n prime should be n plus m prime. And then the set of all integers is denoted by this letter z, and it's the set of all such equivalence classes. And the letter z is used historically because it comes from the German word Zahl, which means number, and Zahlen means counting. So that's the origin of this symbol. So let's see an example. The equivalence class containing the ordered pair 1 1 is an integer, and it's a set being an equivalence class, and it's the collection of all ordered pairs m comma n such that 1 1 is related to mn, which translated means that 1 plus n is equal to 1 plus m. So by the additive cancellation law, the 1 cancels, leaving n is equal to m. So it's the collection of all ordered pairs mn of natural numbers where m and n are the same natural number. So this is the set 1, 1, 2, 2, 3, 3 and so on. So this can be depicted pictorially as follows. So here is sort of the x-axis, here is the y-axis, and over here you have the natural numbers 1, 2, 3 and so on, and here also you have the natural numbers 1, 2, 3 and so on. So these orange dots then represent n times n. It's this infinite grid in the first quadrant. For example, this is the point 1, 1, this is the point 2, 2, this is the point 2, 1, this is the point 1, 2 and so on. So then these points are the ones along this diagonal, and all the orange points which lie along this blue line, those points are there in this set, and that represents this integer, which is the equivalence class containing the ordered pair 1, 1. And this later on we'll see is the zero element in the set of integers, zero element with respect to addition once we define addition. And intuitively this makes sense because we introduced the integers by saying that they were solutions to an algebraic equation. So if I take any mn in this equivalence class, then this integer is meant to represent the x which solves m plus x is equal to n. So in this case you have that 1 plus x is equal to 1. So the x is sort of the additive identity which we usually denote by 0. Similarly 2 plus x is equal to 2, so x ought to be 0, and the x is 3 minus 3 which is equal to 0 and so on. Okay, so intuitively this is the zero element in the set of integers with respect to the operation of addition, which will come later on. So when we started our discussion of the integers, we wanted to solve the equation m plus x is equal to n for arbitrary natural numbers m and n. So this was not always solvable with a natural number, but then the hope was that we can extend the set of natural numbers to this bigger class of integers, and then perhaps this equation is solvable. So we would like to view every natural number as if it were an integer. So what we want is a map from the set of natural numbers to the set of integers, so that given any natural number n, I can put on my integer glasses and view it as an integer. But what should this integer be? So let's revisit our intuitive understanding of what an integer is. So if you have an integer, so that's an equivalence class containing an ordered pair where the first entry is a blue box and the second entry is a red box, and these are natural numbers. Then this integer is meant to be the solution of the equation blue box plus x is equal to red box. Now if the integer x in question is a natural number n, all I want is some natural number here in this blue box and a natural number here in the red box, so that this equation is a valid equation, namely blue box plus n is equal to red box. So if I simply put 1 in this blue box, then I can put n plus 1 over here, because then 1 plus n is equal to n plus 1 is a valid equation. So that's what we do. In the blue box I put 1, in the red box I put n plus 1 or sigma n. So the natural number n is sent to the integer, which is the equivalence class containing the ordered pair 1, sigma n. And we will soon see that this is the set containing 1 n plus 1, 2 n plus 2, 3 n plus 3 and so on. And it makes sense because this captures the integer, which is this minus this. So n plus 1 minus 1 is n, and n plus 2 minus 2 is n plus 3 minus 3 is n, and so on. So it makes sense. So let us check that this map is an injective map, so that whenever you have two different natural numbers, then their images as integers are also different. So here is the theorem. The theorem says that the map from n to z, which sends a natural number n to the integer which is the equivalence class containing the ordered pair 1 sigma n, this map is injective. So suppose that m and n are two natural numbers whose images are the same. The equivalence class containing 1 sigma n is the same as the equivalence class containing 1 sigma m. But whenever two equivalence classes are the same, and you take a representative from the first equivalence class and an element from the second equivalence class, then these two are related. So we have that 1 sigma n is related to 1 sigma m, which translated means that 1 plus sigma m is sigma n plus 1. Now the 1 cancels on both sides by the addition cancellation law, and you get sigma m is equal to sigma n. But the successor function sigma is injective, and so we conclude that m is equal to n. So if the images of n and m under this map are the same, then m has to be equal to n. Okay, so let's also show this equality between these two sets. First of all, let's note that any element of this set contains ordered pairs of the following type. Whatever is the first entry, you add n to the first entry to get the second entry. So if I call the first entry as m prime, then the second entry will be n plus m prime. If I take any element in here, let's call it m prime comma n prime, I have to show that it is a member of this set. Okay, but if there is something in this equivalence class, then it's equivalent to 1 sigma n. But that means that 1 plus n prime is equal to sigma n plus m prime. And the sigma n is n plus 1. So by the additive cancellation law, the 1 cancels, leaving n prime is equal to n plus m prime. So indeed, m prime comma n prime, the second entry, n prime, is really n plus m prime. So the second entry is the first entry plus n. So it belongs to this set. Vice versa, if I take something in this set, then it's of the form m prime comma m prime plus n for some natural number m prime, and then I have to show that it belongs to this equivalence class. In other words, it's equivalent to this one. So to check that this element is equivalent to this, what we have to check is 1 plus m prime plus n should be equal to sigma n plus m prime. But this outer sum is m prime plus n plus 1, and this inner sum is m prime plus sigma n, but sigma n is n plus 1. And so the inner sum is also m prime plus n plus 1. And so this is equivalent to this, so that the element actually belongs to this equivalence class. So these two sets are included in each other, and so they are equal. So as an example, let's take the natural number 1 and view it as an integer. Well, the corresponding integer is the equivalence class containing the ordered pair 1 comma sigma 1, and sigma 1 is equal to 2. So we have this integer, and we know that that's then the set comprising 1 comma n plus 1. So the n is equal to 1 here. So you get 1 2 2 3 3 4 and so on. And in our picture, where do these points lie? Well, 1 2 is here, 2 3 is here, 3 4 is this point, and so on. So all these points lie on this line which is parallel to this one, and the orange points on this are the points in this equivalence class. Similarly, the natural number 2 is the equivalence class containing the ordered pair 1 3, and as a set it's the orange points on this line and so on. This corresponds to the natural number 1, this corresponds to the natural number 2, this corresponds to the natural number 3, and so on. And this corresponds to the integer 0, as we have just seen. So as another example, let's consider the integer, which is the equivalence class containing the ordered pair 2 comma 1. Well, what is that? It's the set of all m comma n's, where m and n are natural numbers, such that 2 1 is related to mn. So that means that 2 plus n is equal to 1 plus m. Okay. Now this 2 is really the successor of 1. So that's 1 plus 1. So one of the 1's will cancel on both sides, leaving 1 plus n is equal to m. So the m here is really n plus 1. So these are all the ordered pairs n plus 1 comma n, where n belongs to the set of natural numbers. So for example, when n is equal to 1, you get 2 1. When n is equal to 2, you get 3 2, and so on. And where are these points? Well, here is 2 1. Here is 3 2, and so on. So all the orange points along this line, which is parallel to the diagonal, will be the points in this equivalence class. Okay, and later we'll see that this is actually the integer which, when added to the integer 1 corresponding to the natural number 1, gives rise to the integer 0. So this is the negative of 1. Similarly, the equivalence class containing the ordered pair 3 1 will be all the orange points on this line, and that will correspond to the negative of this integer 2. And so on the one hand, you get all the positive integers, which are really the natural numbers. Here you get 0, and then you will later see that all of these are the negative integers, such that when added to the corresponding positive integer, you get 0. So you see that the number line is starting to appear over here. Here is 0, here is 1, 2, 3, and minus 1, minus 2, minus 3, minus 4, and so on. Now, the reason that we define integers in this very careful manner with equivalence relations and so on is because we want to prove properties of the integers with respect to its arithmetic operations of addition and multiplication, which are easier to do with this definition rather than some other construction. So we now turn to addition. How is addition of two integers defined? Well, integers we know really are equivalence classes of pairs of natural numbers. Okay, so suppose you have two integers, namely the equivalence class containing the ordered pair m comma n and the integer which is the equivalence class containing the ordered pair k comma l. Then we define the sum, the integer sum of these two integers as the equivalence class containing the ordered pair m plus k n plus l. Now, the first thing that we want to ask is this well defined? Now, this is really a set of which this ordered pair is just one of its members. Similarly, this is really also a set which contains k comma l as just one of its elements. And now I am defining an operation where I just pick two of the representatives from each of these equivalence classes and I use it to define something. But then, okay, I chose mn, but somebody else might choose m plus 1 comma n plus 1, and somebody else might take k plus 3000 and l plus 3000. Okay, and then this ordered pair that I get and this other person gets are completely different. But then we have to check that the equivalence class that we nevertheless get is the same. Okay, so this is the question of well-definedness, and let us check that this integer addition is well-defined. Okay, so to reiterate, the question is like this, that if I take any two representatives from this set, say mn and m prime n prime, and any two representatives from this set, say kl and k prime l prime, then the result which is obtained over here, namely this ordered pair, when I use mn and kl, that should be equivalent to the result I get over here if I use the representatives m prime n prime and k prime l prime from over here, so that once this is true, then the equivalence class of this one will be equal to the equivalence class of this one, and so the resulting integer will be the same. Okay, so this is a question, namely if mn is equivalent to m prime n prime and kl is equivalent to k prime l prime, then is m plus k n plus l equivalent to m prime plus k prime n prime plus l prime. Okay, so what we know is that these two are equivalent, so we know that m plus n prime is equal to n plus m prime. That's what I've written over here. Similarly, since these two are equivalent, I know that k plus l prime is l plus k prime, which is what I've written over here. And what I want is m plus k plus n prime plus l prime is equal to n plus l plus m prime plus k prime. But this one obtains by simply adding these two. After all, if I add these two, what do I get? I get m plus n prime plus k plus l prime. So m plus n prime plus k plus l prime. So this is just the rearranged sum that one obtains on the left hand side. And on the right hand side you get n plus m prime plus l plus k prime. So n plus m prime plus l plus k prime, and again that is exactly a rearrangement of this. So simply by adding these two you get this thing, which is exactly the same as saying that m plus k n plus l is equivalent to m prime plus k prime comma n prime plus l prime. So indeed this is equivalent to this, and so this is a well-defined operation. So it doesn't matter which representative you take from each equivalence class, the answer as an integer that you get is the same. Although this inner ordered pair might depend on who is choosing what representative, but once you take the equivalence class of that, the answer that you obtain is the same. As an example, let us consider this. This was supposed to be the zero element. Long ago we suspected that. Let's check that indeed this acts as the zero element. So this, if I add to any integer, I should get back the same integer. Well, by definition, 1 1 plus the integer which is the equivalence class containing the ordered pair mn will be, well, I simply add 1 and m and 1 and n, and then I have to take the equivalence class corresponding to that. Now the question is this the same as the integer I started off with? Is this the same as the equivalence class containing the ordered pair mn? Well, two equivalence classes will be the same if this element in here is equivalent to this one. So the real question is 1 plus m comma 1 plus n equivalent to mn? To check whether this is true, we have to find out if 1 plus m plus n is the same as 1 plus n plus m. And of course this is true because of the various laws of addition. So indeed this integer added to this one is equal to mn. Okay. So this indeed serves as the identity element with respect to addition, in the sense that if I add that to any integer, I get the same integer that I started off with. Okay, so we defined the addition of natural numbers and we denoted the operation with a plus sign, and now we have defined the addition of integers and we use the same plus symbol. Now this is not strange because it turns out that if you take two natural numbers and add them as natural numbers, and you get a natural number, their sum, and you view that as an integer, the answer that you get is the same if you first view those two natural numbers as integers and add them as integers. So sort of more concretely, for example, let's consider you have the pair of natural numbers 2, 3. So if I add them, I get the natural number 5. And then I can view it as an integer, the integer corresponding to the natural number 5. Now that integer is the same as one obtains if you consider the 2 that you took as an integer, the 3 that you took as an integer, and you add those two integers. Then the answer that you get is the same as the integer corresponding to the natural number 5. So what we mean is that if I take two natural numbers m and n and add them as natural numbers, then you get m plus n. So this is a natural number. Then I put on my integer glasses and view this as an integer. Well, then that's this integer, the equivalence class containing the ordered pair 1 sigma m plus n. Now that integer is the same as one obtains if one first views this m and n as integers. So then m is really this integer, n is really this integer, and you add these two integers, then you get this integer, and that's the same as the integer corresponding to m plus n. So of course this needs a proof that this integer is the same as this integer. This needs a proof, and let's prove this. So let's start with this one. So that's the integer sum of these two integers. Well, by the definition of integer addition, you have to take the equivalence class containing the ordered pair obtained by adding these first components, so 1 plus 1, comma, sigma m plus sigma n. This sigma m is just m plus 1, sigma n is just n plus 1. So you get this integer. Now I claim that this integer is the same as this integer, where I have sort of removed one from both of these. Okay, so let's quickly check why this is true. So I have to check that this ordered pair is equivalent to this ordered pair. So I have to show that 1 plus 1 plus this thing is the same as this thing plus 1. Okay, so let's write it down. The 1 plus 1 plus m plus n plus 1. So 1 plus 1 plus m plus n plus 1. The question is that the same as m plus 1 plus n plus 1 plus 1? So m plus 1 plus n plus 1 plus 1. So you see there are three ones over here which I have highlighted, and here also there are three ones. You start with m plus n and you add 1 plus 1 plus 1 on both sides, and then using the associativity and commutativity and all that, you indeed have that this is equal to this. So this ordered pair is equivalent to this one, and so the equivalence class containing this ordered pair is the same as the equivalence class containing this ordered pair. But what is this? This is 1 comma the successor of m plus n, which is exactly this one. So we started from here and you ended up with this one, and so these two are the same. So if you add two natural numbers as natural numbers and then view the answer as an integer, what you get is the same as you first view the two natural numbers as integers and add them as integers. Okay, so it makes sense to use the same symbol for both natural number addition as well as integer addition. So as another example of integer addition, let us take any integer which we denote by a, and that's the equivalence class containing the ordered pair m comma n. And let us consider now the equivalence class containing the ordered pair n comma m. So I simply swap these two. Okay, and the resulting integer I denote by minus a. So this has no other meaning other than the notation for this integer. And let's add the two and see what we get. Now, by the definition of integer addition, this will be the equivalence class containing the ordered pair n plus m, comma, m plus n. Now I claim that this integer is the same as this one, which we had seen earlier was the additive identity. Let's denote that integer by 0. So this is the equivalence class containing the ordered pair 1, comma 1. So I'm claiming that this is the same as this. So to check that, I have to check that this ordered pair is equivalent to 1, 1. And that is clear because you see that n plus m plus 1 is actually m plus n plus 1. So this is equivalent to this one. In other words, the equivalence class containing this ordered pair is the equivalence class containing this ordered pair, and this is what we call 0. So what we have discovered is that no matter which integer I take, if I swap these two and consider that new integer, then when it is added to this one, you get the identity element. So this is then called an additive inverse of A. And in fact, later you will see that this integer addition is commutative. So if minus a plus a is 0, then also a plus minus a is equal to 0. So for any natural number n, the corresponding integer is the equivalence class containing the ordered pair 1 comma sigma n, and that we denote by this boldface n. And then minus n will be the equivalence class containing the ordered pair with these two swapped, so sigma n comma 1. And these are referred to as the positive integers and these are referred to as the negative integers. Okay, so over here this is bigger than this one, over here this is bigger than this one, but when they are equal, then you get this equivalence class, which is the 0 element. This was just some notation. So as I mentioned in the exercises, you will see that addition is commutative. In other words, for all a and b's, which are integers, a plus b is equal to b plus a. So I use boldface for integers, and of course then we know that they are really equivalence classes containing pairs of natural numbers and so on, but for succinctness we simply write it like this, we're using boldface. And addition is also associative, which means that for every a, b and c, which are integers, a plus b plus c is the same as a plus b plus c. So I first do b plus c, I get an integer, and then if I add it to a, the answer is the same as if I first add the integers a plus b, I get an integer, and that I add to c. Okay, so this you will see in the exercises. But let us now prove the following theorem, which had initiated the whole discussion. Namely that if you have any two integers a and b, then there exists a unique x, which is an integer such that a plus x is equal to b. So we had started our discussion by saying that, well, if m and n are two natural numbers, then we may not always be able to solve m plus x is equal to n, where x is a natural number. But now this theorem is telling us that whenever you have data which are integers, any integers, then you can always find an integer solution, and in fact this integer solution is unique. So let me explain this notation. This symbol we know stands for there exists, and when you put an exclamation, we mean that it is unique. So there cannot be two x's which satisfy this. Alright, so let's prove this. Let's first prove the existence. So simply take x equal to minus a plus b. Well, if a is any integer, we know what minus a is, right? That the thing which is obtained by swapping the members of any representative in this equivalence class. Define x to be equal to minus a plus b, okay? And this is integer addition now. Now let's see that this integer in fact solves this equation. So let's do a plus this x is minus a plus b. And since the integer addition is associative, I can first choose to add a and minus a. But that we have just seen is the 0 integer, and 0 is the additive identity, so that 0 plus b is b. So you have got that a plus x is equal to b. Now let's show uniqueness. So suppose that there are two integers x and y, such that a plus x is b and a plus y is also b. Okay, so then you get a plus x is equal to a plus y. If I add the integer minus a to both sides, then I get minus a plus x is minus a plus y. Again, I use associativity, I club these two together. I have minus a plus x is minus a plus y. But minus a plus a is 0, so you get 0 plus x is 0 plus y. But 0 plus any integer is that integer in question, so you just get that this is x, and 0 plus y is likewise y. So you get x is equal to y. So this completes the proof that the solution is also unique. So there exists a solution and it is unique, hence proving this theorem. Finally, let us show that any integer is either a positive integer or a negative integer or 0. Okay, so recall that we had learned that integers of the type 1 sigma n for an n are the positive integers. This is of course the 0 integer, and the minus of such things are what we call the negative integers. So these are of the form sigma n comma 1 for n in n. So let's show that any integer is one of these three types and these are mutually exclusive. So exactly one and only one of the following three statements holds is what we want to show. So let's first show that if one holds, then two can't hold. Okay, so suppose that both of these hold, that means that A is this as well as this, that means that these two are equal. Well, if these two are equal, that means that these inner things are equivalent to each other, which means that 1 plus 1 should be sigma n plus 1. 1 plus 1 should be sigma n plus 1. By the cancellation law, we have that one of the ones goes away and you get 1 is equal to sigma n. That means that 1 is the successor of some natural number, which violates the first Peano axiom, and so we have arrived at a contradiction. And so if 1 holds, then 2 cannot hold. Now let's show that if 3 holds, then 2 does not hold. Now if 3 holds and 2 holds, then we will have that this and this are both equal to A, so they are equal to each other. So this is equal to this one. That means that this inner thing is equivalent to this inner thing. So that means that sigma n plus 1 is 1 plus 1. Again, the 1 cancels, leaving sigma n is equal to 1, which is again a contradiction because 1 is not the successor of anything. Okay, so 2 cannot hold, so 3 implies that 2 does not hold. Okay, and finally, let's prove that if 1 holds, then 3 cannot hold. So suppose that both 1 and 3 hold. That means that both of these are equal to A. So this is equal to A and this is equal to A, which means that 1 sigma n, the equivalence class containing that ordered pair, is the same as the equivalence class containing the ordered pair sigma m comma 1. So that means that these two are equivalent. So 1 plus 1 is sigma n plus sigma m. Now this sigma m is m plus 1. So one of the ones cancel, leaving 1 is equal to sigma n plus m. But by the definition of addition, this is sigma n plus m. Okay, so you have got again that 1 is the successor of some natural number, which is of course not true. And so 3 cannot hold. So this means that if 1 holds, then 3 does not hold. And by the contrapositives, we also know that if 2 holds, then 1 does not hold. If 2 holds, then 3 does not hold. And if 3 holds, then 1 does not hold. Okay, so this means that each of these is mutually exclusive. Okay, so at most one of these statements can hold. And now let's prove that one of them has to hold. The integer A is an equivalence class. So let us suppose that it contains an ordered pair KL. So the ordered pair KL belongs to this equivalence class, which is really a set. Now K and L are natural numbers, so by the trichotomy law for natural numbers, there are only three possible mutually exclusive cases, namely either K is strictly less than L, or K is equal to L, or K is strictly bigger than L. So one of these three things has to happen, and only one of these three things happens. Now we'll show that this corresponds to this first case. If this happens, then we are in the second case, and if this happens, then we are in the third case. Okay, so let's start with this one. K is strictly less than L. That means that there exists a natural number n such that K plus n is equal to L. Now there are only two possible cases, either K is equal to 1 or K is not equal to 1. Let's consider these two cases separately. If K is equal to 1, then this reads 1 plus n is equal to L. In other words, sigma n, this is sigma n, is equal to L. So A, which was the equivalence class containing the ordered pair KL, well, K is equal to 1 and L we have just discovered is sigma n. And so we have got that A is of this form, so it's a positive integer and we are in this case. Now let's suppose that K is not equal to 1. In that case, we know this theorem which says that every natural number not equal to 1 has a predecessor. In other words, this natural number is the successor of something. So this K being not equal to 1 is the successor of some natural number K prime. So then this equation reads sigma k prime plus n is equal to L, but sigma k prime is k prime plus 1, so you get k prime plus 1 plus n is equal to L. Now A is the equivalence class containing the ordered pair KL, but now this K is the successor of K prime, so that's K prime plus 1, and L we have discovered is K prime plus 1 plus n, so it is this one. Now we claim that this is equal to the equivalence class containing the ordered pair 1 sigma n. Okay, so what we have to check is that this ordered pair is equivalent to this. Is that true? Well, for that to be true, you should have that K prime plus 1 plus sigma n should be K prime plus 1 plus n plus 1. And that's of course true, because you have K prime plus 1 plus n plus 1, and you have K prime plus 1 plus n plus 1. So indeed, this is equivalent to this, and so the equivalence classes are the same. So you have got that A is of this form, so it's a positive integer, so we are in case 1. Now let's suppose that K is equal to L. Okay, in that case you have that A is really K comma L, but L is the same as K, so you have this. Now I claim that this is really the zero integer. And why is that? Well, to show that, you have to show that kk is equivalent to 1 1, but that's clear because k plus 1 is indeed equal to k plus 1. So then we are in this case. And finally, if the third thing happens, if k is bigger than L, then let's note that minus A will be the equivalence class containing the ordered pair LK, right? And we are then in this case where the second entry is bigger than the first entry. You see, the second entry is K, and that's bigger than the first entry. So this we know by this first case is of the form 1 comma sigma n for some natural number n. Okay, and so we have got that A, which is minus of minus A, right? Because if I swap these two, then I get back the A, right? And so A is equal to minus of minus A, and that is the thing that you obtain when you swap this thing, because this is what minus A is. So this is the equivalence class containing sigma n comma 1. So this completes the proof of this theorem. So next time what we'll do is we'll define multiplication in Z and the order relation in Z, and then we will start our discussion also of the rational numbers Q.